Hello and welcome. My name is Florian Pfaff and I'm from the Intelligent Sensor Actuator Systems Laboratory in Karlsruhe, Germany. In this talk, I'm going to present a new grid filter for the unit sphere, which can handle arbitrary system and measurement models. This is joint work with my colleagues Kyla Lee and Uwe Hanebeck. Let's start off with some motivation about estimation on periodic manifolds and why it's tricky. Periodic manifold is something that if you start somewhere and you go along it, you will arrive at the origin again. And there are high dimensional versions such as the hypertorus where you have multiple ways. And then there's also the sphere and the hypersphere where there are many different ways to go along this. And it's actually much different than the hypertorus because it doesn't have any hole. So why is it tricky? I mean, if you have two measurements, just 60 and 300 degrees, and you would take a classical mean, then you would arrive at 180 degrees, which is not really what you want. Because in this case, it's obviously 0 degrees that would be correct. And this is just not a hypothetical problem. If you have a prior density with its mean at 60 degrees and likelihood function with its mean at 300 degrees, then a Kalman filter naively applied would give you a new density with its mean at 180 degrees. This, however, is not a problem of Bayes formula. If you apply Bayes formula, you will get something that has its mean by 0 degrees if you apply it correctly. So where are the research questions and what has already been solved? I would say the circle is pretty much solved. We've presented filters based on trigonometric polynomials and filters based on grids that can handle a circle very well. Because of the low dimension, you can use so many parameters in relationship to its dimension that you can handle everything except degenerate case as well. For the hypertorus, the trigonometric polynomial based filters work very well, but you have to pay attention that it will blow up for high dimensions. For the sphere, filters allowing for arbitrary number of modes have not been presented in our previous filter that we gave. We had the problem that, well, there is no convolution on the sphere, so we only supported easy system models that can include deterministic rotations and noise densities with zonal densities. This means it's rotationally symmetric. So all points at a certain distance from the origin have the same probability mass. But that doesn't cover every case, because if you want to track something that's moved by the winds, then you will have something like that, and that's definitely not something you can model with just a single rotation and then a zonal density on top. So, but even if there's no convolution, you can apply the Chapman-Kolmogorov equation. So let's give an overview over the filters that are currently in existence. If this is the density we start out with, and we use a von Mises-Fischer filter, we always approximate with that unimodal von Mises-Fischer density, so which is a coarse approximation. Well, you always have a PDF, and using some extensions, you can use arbitrary system and measurement models, but you can never support multimodalities. Runtime can be from very fast to not so fast if you use the extended versions. For the particle filter, you can have arbitrary models for the prediction and for the update step. You can have multimodalities. You will just get then clusters of your particles in these different modes, but the runtime is not as good, and you do not get a continuous PDF if you compare it with the spherical harmonics filter that we've recently proposed, in which we approximate the density using certain kinds of functions, which I will get to in a moment. And here you always have a continuous PDF. You can use it for arbitrary update steps. You can consider multimodalities, have good runtimes, but its downside lies in the prediction step because that is pretty limited. So we're going to give a brief summary of the spherical harmonics filter because our filter uses some aspects of it. The spherical harmonics filter represents a density as a double sum of weighted spherical harmonic functions. Here you can see them. I mean, there are different functions for different degrees. This is degree 0, this is degree 1, this is degree 2, and for all of these there are functions of different order. Sometimes the terms are swapped in the literature, so don't get confused when you read that there. So, but here you have a constant function. Here you have one that just changes once along each axis. And then you have some that have a mixture. So the more and more coefficients you take, the more and more accurate your approximation can become. This also shows here. If I just say, well, I just take only these ones, then I just get this unimodal thing here. And the more and more functions I include, the better it becomes until I'm visually indistinguishable to the original solution. For the update step, well, I could stay in this coefficient representation where I just have these C's, but the fastest formula I've been able to derive was that it's an O of n to the power of 2.5, just if I just stay in this representation. However, I can do it via a grid in n log n square. So this is why I've actually switched back to a grid filter for the update step. Why did I even consider the spherical harmonics? Well, it's good for the prediction step. For the simple models that just have a rotation and some additive noise on it, it's accurate and very, very fast. That's just no offense. Well, a downside here is that, well, you cannot use it for arbitrary transition densities that easily. This is why we now consider grid-based filters that stay on the grid the entire time. But before we get to prediction and update steps, let's first consider what do the grid values mean. Well, the grid values can, for example, mean the probability mass that is in a region. So the grid value here would be the probability mass in this entire region. So you can obtain this y integral, which is actually pretty expensive. The second interpretation would be, well, we have the function values of a continuous density at the grid points. Such a grid could look differently. You could have an equiangular grid, where you say that you just go along the azimuth and the elevation angle and consider all grid points to lie on these lines. Or you can have equidistant grid where you say you want to move the grid points far from each other relatively. And if you increase the number of grid points, you see that you get a pretty dense mesh here. In these plots, I've shown the function values as the size of these circles. But then we have to consider how do we interpolate them to get a continuous density. So let's consider some possible interpolations. If we have the original density here and we take the function value at 18 points and interpolate it by saying that, well, it's actually constant in every region, then we get a function like this. I mean, this is non-negative everywhere, but this does not really resemble the original density if you ask me. So as an alternative, we can do a smooth interpolation, one that actually may have negative function values in this variant, by taking this vector of grid values, applying a spherical harmonics transform to it to get a matrix of spherical harmonics coefficients. This will allow us to use this spherical harmonics to get a smooth interpolation that I think resembles the original density really well. Then we can change it in a way that it does not have negative function values. How do we do that? We'd first take the square root of the function values on the grid, then use this and interpolate this with a spherical harmonics transform to get a matrix representing the square root of the function. Then if we have the spherical harmonics, then we can square the result to get an approximation of the original density, which is now in this case pretty close to the other one, but it's always guaranteed to be non-negative. But there's one caveat. You have to pay attention that the values, these grid values, are always non-negative, but this is ensured in our filter. So how can we implement Bayes' formula? We now have these grid values shown in the size of the circles again of the prior density that corresponds to this interpolated density. And we've got the likelihood. And we need the likelihood function on the same grid points. So you could actually interpolate the likelihood, although you will never really need for the filter. And then we just do a pointwise product. And this gives us the result for the unnormalized posterior density. It's non-negative, definitely we just multiply non-negative values. And it's proportional to the two values because we have just the function values on the grid points. And just for these function values, it's precise. What's not precise is that after the normalization. One issue here is that if we have a likelihood function that makes the density more concentrated, that concentrates all of the density in a very narrow area, we're going to lose all of this because we do not consider a likelihood function on that high of a grid. And even if the likelihood function is really absolutely considered perfectly based on the grid values, then you have to keep in mind that just like in the Fourier series, if you have two signals with a certain number of Fourier coefficients and you multiply them, you will need additional Fourier coefficients to actually represent that multiplication result. So let's get to the prediction step and I'll briefly give the key ideas based on the one-dimensional case because it's much easier to visualize there. So we've got that posterior density from the last update step. It's just depending on one variable, but let's just say this is dependent on two variables. There's another variable of that future time step that our function is currently invariant under. And then we've got the transition density that is both variant on the current and the next time step. Then what this is here, this is just like a joint density that we obtain if we multiply these two functions. All we have to then do is perform this last step, the marginalization, to obtain the predicted density for the next time step. To explain the prediction step on the sphere, I first visualize the transition density on the sphere. For this, we interpret the transition density as a function on the Cartesian product of two spheres, and then say we condition on the current time step, and then provide a density that is interpolated here for the next time step to obtain a transition density that can be as shown here. Now we proceed as in the one-dimensional case, and for every grid point, we consider the predicted density at a certain grid point. And for this, we multiply the posterior density of that time step with the transition density for the fixed value of the same grid point that we enter there. And then we sum them all up, which we then average using this factor to perform the marginalization, which yields the formula 4 pi divided by n multiplied with the sum of all these of the transition density where we iterate through the columns multiplied with the respective value of the posterior density of the previous time step. And we can actually then get the entire vector by performing a matrix vector multiplication of the transition density with the posterior density of the previous time step. But for the sake of time, I won't show this in detail. And the non-negativity is always preserved here because we're just multiplying non-negative values and summing them up. So, and to conclude this, let's look at a scenario that is very well suited for Mises Fisher filter. Here we can see that our grid filter converges to the optimal result much faster than a particle filter if we consider this as a per number of parameters. So meaning we need much less grid points than the particle filter needs particles to achieve a very good quality. Actually, we can even surpass the von Mises-Fischer filter because we can maintain the optimality over multiple time steps, whereas the von Mises-Fischer filter can not be 100% optimal throughout the prediction steps. And regarding the runtime, it's also faster than the particle filter because our spherical grid filter just rises very, very slowly. We have very, very high efficient operations because we just have some multiplications there, and we do not need to sample from the density as the particle filter does. To sum this up, we've got a very fast and versatile filter with a spherical grid filter. We can always provide valid continuous density via an interpolation, and we have something that's easy to generalize even for higher dimensions. As an outlook, we could work on a faster prediction step that uses the equivalence to spherical harmonics to do some certain prediction steps there in a faster manner. And we could consider topologies, for example, the hemisphere and hemihypersphere that is very useful for quaternion estimation. So thanks a lot for your attention. I'll be happy to see you in the Q&A session.